Swayam Prabha. Digital India. Educated India.
Good morning, everyone. It is my honor to welcome Professor Rajesh Singh, who has years of experience, deep subject expertise in physics, and a genuine passion for teaching. He did a PhD in the Institute of Mathematical Sciences, Chennai. His research interests are in the field of theoretical soft condensed matter physics. Professor Rajesh Singh has not only imparted knowledge but has also ignited curiosity in countless young minds. He continues to be a beacon of excellence and a role model to many. We're truly grateful to have you with us. Thank you.
Right, so thanks for the introduction. So, how many of you are in 11th class? You're going to 12th, right? Okay. Do you know what is Reynolds number?
Yes.
Right, good.
We learned it last year. Fluid mechanics.
Right, so my research involves a lot of and what else do you know? You know Newton's equations?
Yes.
Right. Okay, so my presentation today and tomorrow is going to be based on a paper which was written by Purcell. Have you heard of Purcell? He got Nobel Prize for discovering NMR, and he has an excellent book on electricity and magnetism, which probably you'll study this year, or maybe a year after that. And he wrote a very nice article on life at low Reynolds number. So that's what I'm going to be telling you about today and tomorrow. And yeah. So I kind of assume that you don't know what is Reynolds number. So I'll introduce it in the way I understand it better. And so let's start with a slide on length scales, right? So we know that, and again, I'm going to come back. If I ask you a question that, you know that the matter is made up of atoms, right? How many of you have seen it? How many of you have seen atom? I mean, how do you know matter is made up of atom, right? Everything looks so continuous. Do you know the answer to this question? I mean, did someone tell you? How do you know, right? I mean, someone. Yeah, exactly, right?
Everyone told us.
Excellent. So we'll talk about that for those who don't know and so if we assume that matter is made up of atoms, so atoms are very small, and as you go on increasing the length scales, you have this viruses and bacteria and like, you know what is milk? Have you studied any electricity and magnetism? Charges repel each other, right? What is milk? Do you know what is milk? What kind of, and how do you make paneer out of milk?
Put lemon into it and boil it.
Right? So how does that happen? Why do you need to put lemon in milk to make paneer? Uh-huh. Okay, but so, I mean, milk is mostly water, right? Why does it look white? So these are basically, do you know that our body is made up of DNAs and things like that? And DNAs are also charged. Do you know DNAs are charged, right? And in a very, very little volume, you put lots of charged particles together. How do you do that? Yeah, how do you condense? How do you condense lots of charged particles? Because in your electrostatic course, you saw that if you put 2 point charges, they repel each other with 1/r interaction. The potential is 1/r. It decays very, very slowly. And it's actually the same way, like basically milk is like lots of charged particles, say positively charged, for example. And because they repel each other, they distribute themselves very uniformly. And they are of the size of the visible range of electromagnetic spectrum, so it looks white. But what happens when you put the lemon? Okay, so you think about this maybe, because I'm also going to talk to you tomorrow, and so the one of the main theme of my talk. I mean, today, I hope by the time I'm done with today and tomorrow's lecture, you have more questions, and then you think about questions. So that's the idea. Okay, so colloids are very small, and that's the length scale we are interested in. Bacteria, human hair is about 70 micron, and you're talking about something which is 1 micron, which is like 70 times smaller than human hair, and they are very, very important. They're very, very important. So just to give you some idea, a micrometer is 10 to the minus 6 meter. Human hair strand, the typical width of the human hair is 70 micron. And how many cells are there in your body? How many microorganisms are there in your body? Huh? So basically, I mean, my research, I spent a lot of time thinking about this microscopic object like milk or bacteria or these microbots you can make, those kind of things. That's what I spent a lot of time thinking about. And so like some of you might know this. So at least when I was a student, I used to get very confused with this millions and billions, because I was used to thinking in terms of 100 lakhs, and so I just thought I'll show you that very, very quickly. So 1 million is 10 raised to the power 6, billion is 10 raised to the power 9, and trillion is 10 raised to the power 12, right? So that is, I think, easy to understand. A human body has about 30 trillion cells, but we have 39 trillion microorganisms, and they live in and around us. So basically, they are helpful. Many of them are helpful. Some of them are not. And to understand that, I mean, we're still trying to understand that. So that's why studying these small objects is important. And there are other regions which I will tell to you about in a minute. And so this is what I was telling you. I mean, the theme of my talk is this quotation from Einstein that I just want to keep asking questions. And that's what I also want you to do. I want you to keep asking questions. Like in the business of the kind of business we are in, creative science, questions are more important, right? And you keep thinking about a question, that's what keeps you going. And so Einstein said that, like in science, right, when you're doing research, you have to do something which nobody else has done, and you don't have to take anybody's word for it. And that's why, I mean, like, that's the idea. It's like, if you keep asking the question correctly, you get the correct answer. I mean, that's what Einstein is saying, that if I have 1 hour, this is basically like, I think George Washington said that if I have to cut a tree with an axe, I have 1 hour, 50 minutes, I will sharpen the axe. And then last 10 minutes, I'll cut. Same way, if somebody asks you a question, think about the question. I mean, especially, I'm not talking about exams, when you only have 1 hour to write the exam. But if you have to solve a big problem, right? For example, how did life start on Earth, right? We still don't know the answer. It's a very big problem. So you think about how, and you ask 10 different questions, right? And then so like Einstein also made another statement, which I think was very, very remarkable, is it's not that I'm so smart, but I stay with the questions much longer. I mean, you have to spend time with the question. I mean, I know for all our school system teaches this. You have to quickly write lots of answers, and all that is important. But if you spend more time with the question, you go in more depth. I mean, that's what I feel it's all research is about. You keep thinking deep, and you get your answer, right? So another question which Feynman asked. You might have heard of Feynman. He got a Nobel Prize for quantum electrodynamics. And he, in 1959, he came up with this idea that what if we can swallow a doctor? Like, basically the idea that many times when you eat medicines, it does lots of harm. It doesn't directly act where it should act. So if you ate a colloidal particle, something which is very small, which can go inside your vein and basically moves and goes where the problem is and fixes it, Targeted drug delivery is the buzzword. And people are doing some of these things. And another reason why you should study these small particles, right? Like for me, because I'm a theorist, for me, I mean, applications are good, right? But also more fundamental questions. So you have studied some thermodynamics. What is the pressure of a box of a gas? PV is equal to nRT. You decrease the volume, the pressure
increases.
right? So if suppose you have a tub of water, you have a tub of water. You have this tub, and there is a water, and you put a object like this, and you fixed it so that it doesn't fly away, but it can turn, right? And then you attached a weight to it. If you just put it in water, can you, huh? It's inside the water, and so like this is basically I'm looking from the side, this is my tub of water. And if I put, so this is my floor, can I lift a weight using this? Like this kind of questions, because can you do some work using this kind of this kind of question? So like even before I get there, what is the pressure of a box of microorganisms? Someone gave you a box of microorganisms. What is the pressure of that? How does that change with temperature, with volume, right? It may sound like a crazy question, but you know, I'm like Einstein came up with his theory of relativity by asking the question, what happens if I sit on a light and go around the universe? So I mean, asking these kind of crazy questions is good. You should ask questions, and by the way, you should ask questions. I always say in the class that many students feel like, oh, I don't ask this question because it's stupid. I think if a teacher is saying the question is stupid, probably they don't know the answer. Because the thing is, if I know the answer, you ask a question, I'll be very happy to answer, right? And I mean, I like this business of teaching because I get to learn. Many times I go to a class which I think, oh, I know this subject very well, and a student asks a question, I don't know the answer. And that makes me very happy. Okay, good, I learned something new, right? So that's, I ask you to ask questions. So what is the pressure of a box of microbots? And that's the question which I, for example, have been trying to answer myself and for last 5-6 years, and haven't made much progress. But yeah, I mean, we also do other things, and many times much of the science is not planned. So this isn't the same experiment which I was just telling you about. So have you heard of E. coli bacteria? Yes. How does an E. coli swim? So why does it need a flagella to swim? Suppose if E. coli had a shape like this. I mean, you know how does if you go to the Marina Beach, right? In Marina Beach, how does a boat swim? So like there is a boat, and I'm bad at drawing. There is a boat. At the back of the boat, there is basically a thing like this which moves up and down. Rudder. Why does E. coli need to have a flagella or very complicated structure? But I mean, this is a simpler. Like, I mean, somebody had to make an E. coli. Why did they make it so complicated? So I mean, here also, I mean, this works, right? They use it to move the boat everywhere. Why does an E. coli need to have a flagella? So again, I mean, these are questions, right? You should have thought. If someone told you E. coli moves because of a helical flagella, why does it need a helical flagella? Okay, I mean, so like I said, I am not looking for answers very, very quickly. But if you have not thought of it, think about it. Maybe think about it today, and tomorrow again we can discuss. So E. coli, by the way, are inside us as well. And so Robert Di Leonardo in Italy did this experiment. He took a bath of, so he took this experiment and he put some E. coli in that. So there's a tub of water, he put some E. coli, and he put the same thing, and this thing starts turning. So basically, if you now put a load, then you can lift it. You can lift the load because this thing is turning in one particular way. Basically, what is happening, and this is the reason. Suppose if someone said that, I mean, I don't know what I want to say, but if everybody is quickly running to the door, there will be a jam, and it will take you long to come back. So here, because there is this groove, equalize runs, and then they keep pushing, and they don't come out because there is a persistence. A water molecule has no persistence. And so that's how you can get it to do some work. Obviously, E. coli needs to eat, otherwise you would have free engines. So you have to give food and it does some work, it's fine. So it doesn't violate the, say, the Carnot theorem and so on, right? So that's the one big sort of what shall I say, sales pitch of what I do. You can do the physics which you study doesn't really apply very easily to these systems. For example, an E. coli needs to have a flagella. Why, right? Why does it need to have flagella? Okay, so I start now talking about, again, something which you study in the school, Aristotle, Galileo, and Newton. So what did Aristotle say about laws of motion? So, I mean, Aristotle said there is this duster here sitting by itself. If I want to move it, I have to apply a force. So he says that the velocity is proportional to force. That's what Aristotle said. I mean, it made a lot of sense to him. And then Newton came along. Newton said, no, Aristotle, you're wrong. Objects don't move because you apply force. Objects move because of inertia, right? That's what we study. So Newton says inertia makes object move. And who is right? Why? What is inertia? So will I have the same inertia? I mean, what does inertia depend upon? So I have a given mass. Will I have the same inertia always? Or like, I mean, if you ask me, inertia is a very funny concept. When will inertia act? And so when is, and by the way, and I'm not going to talk about it, even Newton is wrong. Einstein's relativity is the most general picture, and Newton's theory is something in between. And I'm going to spend next, I don't know how long, and tomorrow to show that even Aristotle is right in some region, right? So that's how science works. So the way science works is you find some, like Newton came with this idea of something called inertia, right? And then someone told you it's because of mass. And then I'm going to tell you that mass is not it, if there's something else. Probably because I will show you that same object has the same mass, but sometimes it has inertia, sometimes it doesn't have inertia. And what is that? Because suppose somebody is saying, oh, very large mass. So then if something has very large mass, it has more inertia, right? And then I'll ask, how much is large? 100 gram or 1000 gram?
There is a way, like if it has a bigger mass than, like object A has a bigger mass than B, then A is said to have more inertia.
But if I give you one object and it's swimming in water, will it have inertia or not? I mean, so this is one of the key things which I think they don't teach a lot in school. I mean, why do we talk about Reynolds number anyway? What is the big deal about Reynolds number? And why not talk about viscosity? Why do you talk about Reynolds number? No, that's fine. But why? What is this number so important there? So flow is turbulent, Reynolds number is larger than 1. So now you have a handle on things. If something is dimensionless, you can say if it's more than 1, one thing is more, less than 1. If you say mass, I mean, then you will have, you can compare the two things, but a mass is a dimensionful object. Dimensionful objects are bad because you can't say what is more, what is less. Reynolds number, you can say what is more. More than 1 is more, less than 1 is less. dimensionless numbers are very important, and if you don't understand, maybe I'll ask you this question again today, tomorrow afternoon, and it's fine. I mean, I am a very slow learner, and maybe I'm not even explaining it very well, but dimensionless numbers are very, very important. And that's what we are going to answer. So because this is supposed to be, can you try to answer this question? So there is an experiment happening. There is no quantum mechanics. Everything is what you have studied in your school. And someone does actually, this is a true story. This happened back here in a couple of weeks ago or months ago. Somebody was doing this experiment on a colloid, and they found that this colloid at t is equals to 0 was here. They're very far. And as time decreases, they're coming close and so on. And we found in the experiment that x to the power 5 is proportional to t. So, I mean, this is the kind of thing which, again, we do in science. You have a data, and then you try to fit a model to it, right? So, what is, and my claim is that they interact through some UR. For example, if there were one positive and negative charge, the potential is 1 by R. So, because the distance is, so here I am saying that this U, I am saying U is equals to U naught x to the power n. What is the value of n? If I give you x to the power 5 is going as t, what is the value of n? Is the question clear?
What is x?
X is the distance between the particles. So it could be r or whatever you like. Just like if you have 2-point charges, positive, negative will come closer. And there also you could derive some law that the distance is going as a function of time. And that you can derive very easily. I mean, so that is the original problem. You have laws of motion. You know how to do integrations. You can do integration, and you will find that the distance goes as time. Now I'm saying the distance is going as a time like this. Tell me the potential. And what is the answer? If n is 0, then they will not interact. They will stay wherever they are. Is that right? Yeah. If n is 0, then there is no interaction. So there is no reason for the particles to come close. Clearly, n is a non-zero number. And so is there a unique answer? So I'm saying these are colloidal particles. They are not moving at the speed of the light, so that you don't have to worry about. But in this experiment, what should be the potential? And if everybody has noted the question, I'll move on. Tomorrow I'll discuss the answer, and I want you to think about this. This question is, I mean, I found it very, very useful. So, how many of you know about Superman? Have you read the Superman comics? Sure. Yeah.
Does it have to be one answer? Is it possible, after the range, no matter what the potential is, the particles will start moving?
So it seems to have a nice trend, right? I mean, in this time range, whatever time range I've chosen, there the trend seems very nice. So in this range, what is the potential? Because if this thing was doing something funny, then. But because I am saying that the data is very good, I'm not showing you the data, but I'm assuming that data is very good. It's just doing x to the power 5 st. For this small interval of time, when the particles come close, more funny things can happen. But I'm assuming that's why when I drew this picture, I started like this. When they are very far, when they are here, I don't say when they will come very close, maybe other funny things can happen. So I'm talking about the regime in which x to the power 5 is going as t. This is the experimental data given to you. This is the truth. With this truth, what is the potential which makes them come closer? And does it depend upon something like what is the, for example, here I didn't tell you one thing is what is the mass of the particle, right? Mass didn't show up. Like, is, and nobody asked me also what is the mass of the particle. So, right, so tell me what all possible values of n you can get, and then I will give you my answers. You don't have to, again, you don't have to take my words for it. You have to, you just have to convince yourself. Which is, what is that number? 12 or minus 12? Because if it is 12, then it should increase. The interaction will increase when they are far and decrease.
No, minus 1.
You're getting minus 1. What are the other answers possible? So actually this question has several answers, and you should defend your answer. What do you get? Minus because it's so I mean like U naught is negative. It's an attractive potential. So, and so let me also think about this, and tomorrow we'll discuss the answer. I mean, like I said, the whole thing is spend more time with the question. Somebody will give you a question, spend time with it. Think about it. What is going on? All right. So tomorrow I also have a class, so I'll talk about this. So this is the kind of the origin story of Superman. They said that an ant can lift something which is many times its body weight. A grasshopper can jump many times its height. So Superman can also do all this. So why can't a Superman do it? What is wrong with this? I mean, why can't I just rescale the physics? Oh God. Yeah, this is what I'm going to talk about for the next 15 minutes. Yes. So if some of you don't know this, then please bear with me. Others who know. So that's the idea. So I mean, the simple point, square cube law is just one example, but the point is that scaling is not straightforward. The physics which applies at this scale, the same physics will not apply at a very small scale. The physics which applies for grasshoppers will be different from the physics which applies for Superman, unless Superman is made up of some very fancy material. So I'll let me because I have some slides. Let me go through this slowly. So Newton says that because he has seen farther than others, it's because he has been standing on the shoulder of giants, and probably he was talking about hooks, but we'll not get into that. And so the general wisdom is that what he's saying is we build on the ideas of older people who came before them. So it is said that Newton's laws were kind of known in some form to Galileo. So Galileo wrote a book called Two New Sciences. So in 1638, he actually died in 1642, and Newton was born in 1642, which is a very interesting coincidence. And so Galileo wrote a book called Two New Sciences, and so the Two New Sciences had two parts. One of them was on laws of motion, and as Stephen Hawking said that he kind of predicted something like Newton's laws of motion. Newton worked more harder on it and thought for more longer, and then came up with his laws of motion. The other thing which Galileo was working on, and probably he's the first one to think about this, is the science of materials. So the science of material, so science of motion you know very well, and I'm not going to get into that. I'm going to just briefly tell you about the science of material, and this is the so-called square cube law. So it says that the strength of an object, for example, a pillar, its strength is proportional to the cross section, L square. I mean, if you make a very long pillar, its weight is L cube, but strength is L square. So as you go on making it bigger and bigger, just simply scaling it, it will become weak. And so like, you can ask this question, why don't we have humans who are like 5 kilometers long, right? Because if we just scale, our weight will increase as L cube roughly, if we think of us like a cylinder, but the strength of our legs will only go as L square. So we will not be able to support our own weight unless the legs become wider, because so his idea was the strength is proportional to the cross-sectional area, like the width of the column, and yeah, strength is proportional to the cross-sectional area, and area increases L square, volume is L cubed. So if you, for example, if there was a bridge which was made, and if you just scale the bridge 5 times, the bigger bridge will be weaker because its legs are tinier. And like, I don't know if you have seen, but generally bridges are made in a way that they are more thick at the bottom because they have to support more weight. So more is the thickness, more is the strength. That thing is very, very well understood. Similarly, trees can't go very longer. And so the idea is that the principle of similitude, which phrase I took from the book by Darcy Thompson, geometric similarity is not enough. We must also have kinematic and dynamics. It should have the same sort of stability. Just because something looks the same, I mean, we can't make us very small or very big. There is a certain size at which we exist. There is a certain size at which trees exist. So there is, and that is selected from very, very simple ideas. So that was the idea of two-third law, and I personally read it for the first time in this excellent book. I mean, if there is one book, I mean, that's my suggestion. If you're going to read this summer, it should be this book. It's called Scale. It's by Geoffrey West. It's an amazing book. So he has this plot where he plots the so this is data taken from, I think, Olympics, and as the weight of the persons increases. So Olympics, you know that there are different weight categories of weightlifting, and how much weight they lifted, and on the x-axis you have the body weight, and it fits very well with this two-thirds law. Like so this law is not just something which Galileo thought about. It also seems to work very well in real life. That just because somebody is, I mean, so in obviously in Olympics, all the very fit people go. Somebody is 50 kg and somebody is 100 kg doesn't mean that somebody who is 100 kg will lift twice as much as the other person. It will follow the two-third law. And so this guy, Geoffrey West, shows this two-third law in a lot of different settings, and how big should a city be, and so on. It's a brilliant book. So I strongly recommend that you find a copy of this and read it. Right, so physics changes with scale, and physics doesn't allow Superman to lift something many times their size unless Superman is made up of not flesh and bones, but some other very fancy material. I mean, if their legs itself become something different material, then they can do it. Like if you want to make a bridge which is geometrically similar with the previous one, then you have to use a much better material. Like, and earlier people used to make pillars with just maybe sand and so on. Now they use concrete and steel, and even if it's thinner, it will be more strong because the material itself is stronger. All right, so Superman seems to not work. What about Aquaman? What is the law of physics which applies to somebody who is in the water? Because now you don't have to worry too much about, you can lift, I mean, Aquaman can lift lots of, even you, when you go inside the water, you can lift lots of massive weight. And here again, another book suggestion I have. It's a book by Darcy Thompson on growth and form. It's a very good book. And what Darcy Thompson says in his book is this: suppose there is a Aquaman, or there is a fish, or there is anything inside the water. The amount of force they can apply to swim, I mean, how much muscles they have, that's what they need to swim, will go as L cube, right? The muscles they have will go as L cube. And so I'm talking about these big objects. The muscle there will go as L cube. And what do they have to counter? So when you are swimming, you have to move water out of the way. There is some friction. So what is that friction? So what should I balance against what? And so I use this word inertial drag, and you will see that, I mean, inertia is again a very controversial topic as just discussed. So I'll try to explain what is inertial drag. What do I mean by that? So inertial drag goes L square V square, and if you balance the two, then you get V is proportional to square root L. And have you heard of this? This is called Froude's law. Have you heard of Froude's number? You heard of the Reynolds number? Did you hear about Froude's number? And again, like this is a very nice story, again taken from the book Scale by Geoffrey West. So the next 5-10 minutes, I'm going to tell you about Froude's number. Froude's number has a very interesting story. Have you heard of Brunel? So many of you want to do BTech, right? Yes. So okay, so do you know who is your favorite engineer? Who do you idolize? Who was the finest engineer? So, but have you heard of Brunel? Did you watch this TV series Adolescence? No? So this guy says that he really idolizes Brunel and so on, a very smart guy. So who is Brunel? What was he doing? All right, so I'll tell you about Brunel in a minute. So I just want to, yeah. V is the velocity. So let me explain that. So what is the drag force? So the force is that a fluid applies on a moving body in the fluid. So imagine we make this spherical cow approximation, as they call it. Object which is moving is spherical in size. So its cross section is going as L square, and it has to move some fluid out of the way. And what is the volume of the fluid it has to move out of the way? It is L square into the velocity with which they are moving. So in time dt, this much volume of fluid has to move out of the way. L square V dt. I mean, it's very just scaling calculation. So numbers pi I'm not writing. And what is the Newton's? I think one of the laws Newton's is force is rate of change of momentum, right? So rate of change of momentum is mass into velocity, cross-sectional area is pi square, distance moved in time dt is v dt. Thus, the volume of fluid displaced in time dt is pi L square v dt. The mass displaced in time dt is rho, density times, I should also have multiplied g, which I have not multiplied, because mass is rho into, so this is, I mean, the mass changes with gravity as well, but it's a scaling, it's a constant, so I don't worry about that. So from here, I get delta p by delta t is rho L square v square. If a particle is moving with velocity v, and it has typical size of length L, then the rate of change of momentum is similar to rho L square v square. There will be some constant which I'm not taking care of. So v is the velocity. Right, so the Industrial Revolution in England was, and even before that, people used to, like back then, a lot of transport was through ships. So the question is, how do you build ships, aeroplanes, and cars? And this is life at high Reynolds number, and these are very, very important. You need to make a very big ship, and there is a aeroplane you need to make. And so Brunel was one of the finest scientists, like basically an engineer in England, and he made railways and so on. And then one day he came with this idea that so the friction is going as L square, right? And the amount of stuff a ship can carry is going as L cube, right? So he has this very simple idea, right? And he says, if I make a very big ship, I can make a lot of money. Smaller ships are bad, bigger ships are better, right? And so he called this the Great Eastern. It was a massive. It was about. So when it was made, it was the largest ship, 211 meters in size, and today's ships are also only not much longer, maybe 500 meters. And yeah, so he decided this will be used to go farther and take a lot of stuff. And the idea was that large ships are more efficient. And so when you have to put the ship in the water, you need to use some chains, and these were the chains for, it's very big chains he had to make. But the problem, one of the main problems back then was people did not know how to make big ships. Like there was a small boat you make, and that works, and then you make it slightly bigger, and then you make it maybe twice that bigger, but there was no principle. People did not know what to do, how to make a boat, and the only way was to make it and then hope that it'll work, because make this big ship and it should work, it should be stable. I mean, you don't want to put a lot of people in it, it'll go and sink. And this was happening a lot back then. So someone was making a ship like this, and then the king said, so this didn't work very well. The Great Eastern was used mainly to lay transatlantic cables. It never really carried people. Someone else made a ship in the Swedish ship. It's called Vasa. That was made, and the king said, "Yo, you put this thing here. Here I'll put missiles, and here I'll put this and that and so on." And they put lots of stuff and a lot of people, and they put it in the ocean, and then it went 100 meters, and then it sank. So the problem was that there was no law. I mean, what law should I follow? How do I make ship? And like, how do I make a plane, for example, right? I mean, I don't want to make a massive plane and then see if it is stable or not. But then the problem is, physics is not the same at different scales. So what is same? I mean, you understand, right? So that's why dimensionless numbers are very important, because they don't care if you're talking about 1 centimeter or 1 meter. If you keep that dimensionless number same, it will have the same feature. Its dynamical stability will be same. And so this guy Froude comes along, and he says, and we did this very hand-waving argument just now, that V square should go as GL, and this is by his name. So you can also derive this from the so-called Navier-Stokes equation, but I've been told I should not show any partial differential equations. So I just derived it using the Aquaman example. So if you keep V square by GL same, you make a big ship or you make a small ship, and if you keep V square by GL same, it will have the same stability. And so Froude said, I will make these tanks. This is 85-meter tank in 1872, and he'll put a small model of the ship, and he will study its stability. And back then people were not very happy with him. They're like, okay, you want to play with toys, it's fine, we'll fund you, but in his time, I mean, generally when people come up with these ideas, it doesn't directly work. It takes some time. But after that, now obviously people use this similar idea. You make a small sample. You don't just dynamically rescale. Use the same dimensionless number, same Reynolds number, same Froude's number, and then it will behave the same way. Because that does not depend upon the scale. And that's the idea. And another person who came with a great idea to do with ships was Robert Fitzroy. Have you heard of him? Who was Robert Fitzroy? Have you heard of Darwin? Yes. Who was the captain? By the way, I mean, Darwin was not doing very well in studies, and he was supposed to become a priest somewhere. And then Fitzroy was a big guy, and he had this. He had to go somewhere. Actually, it's a very interesting story. Fitzroy was working for this another scientist who said that all this volcano and all these things happen very slowly. Things gets built up inside the earth, and then there is a volcano. This guy didn't want to travel. He wanted somebody else to go and collect data across the globe. And then that guy, so this guy's name I think is Charles Lyell. And that data, something happening very slowly over time. And so Fitzroy wanted somebody to collect this data and dine with him, because hierarchy was a big thing back then. And Fitzroy was going to be gone for 5 years on the ship. He could not dine with people who were the sailors and other people in the boat. So he wanted somebody to dine with. So he took Darwin along. Anyway, Darwin was not happy with his surgery thing. And so Darwin was collecting this data that's slow things lead to bigger things, and then he came up with this. I mean, he looks at lots of birds and so on, and he came up with this idea of evolution. But because Fitzroy was on the ship for a long time, and he realized that if the weather goes bad, you lose a lot of money and people. Like a ship is just about to dock on the port, and just before it's about to dock, there is a cyclone, and so you want to predict weather. So Fitzroy came with this idea that you should forecast weather, and he started making models, basically solving Navier-Stokes equation. And in his time, he was not very successful, but people then took that up, and weather forecasting is a big thing. I mean, especially if you go to England, right? The weather keeps changing very fast, but their forecasting is so well. I mean, in tropics, I mean, we are far away, we are close to the equator, but as you go farther away from equator, the weather is very moody, and good prediction helps. And that was again has similar story and similar equation, the Navier-Stokes equation, which gives the flow of fluids. Water is a fluid, air is a fluid as well. Okay, so this was the idea of Froude, right? Froude said that just keep the same Froude's number, and things will have the same dimension. So you make a small boat, you keep the same Froude's number and see how it's behaving. If it is unstable, make a new model. And you try and test with these models, and same thing you do with the aeroplane models in wind tunnels. So that's why we need wind tunnel. You change the velocity, right? V square by L should be same. So if you're making a very small L, then V has to be very large. So people do this airplane experiment in wind tunnels. They send very fast speed wind, keeping the V square by L by same, and then that can be used to study the stability. All right, so this is all about, I mean, Froude's story is very cool. First person to come up with this idea of dimensionless number, people were not very happy, but then after that people realized you have to make this, say, building tanks and use dimensionless numbers to start making things. Okay, so the last thing I want to talk about today is coasting distance. So you write the Navier-Stokes. So I generally derive this, but you write the equation of motion. So basically, you write the Newton's equation for a fluid parcel. So you go to a fluid, a small volume fluid, and you write Newton's equation of motion. And that equation of motion, the velocity is meter per second, time is seconds. So assume that the velocity is, typical velocity is v. So you replace v by capital V into v star. Now this v star doesn't have any dimension. It becomes dimensionless. And you pull out a number out of the equation. So you non-dimensionalize the equation. And when you non-dimensionalize the equation, a dimensionless number appears in the equation. And that number, so the thing is, if you agree that there is an equation called Navier-Stokes equation that I need to solve to study the stability of a ship or boat or whatever. So if you solve this at a centimeter scale, you'll get some dynamics. You solve it at a kilometer scale, you get some dynamics. But if you just pull out all the numbers and put it in some dimensionless number, and then the dynamics only depend upon that dimensionless number. It will not depend upon centimeter or meter and so on. So that's what I am not doing here.
So then by that logic, from any given equation, we can replace a variable with dimension with.
That's what I want to do. That's what I want you to do for the problem I gave you today. I want you to find a dimensionless number and show that what happens when u0 and so you write the equation of motion, and then you find dimensionless numbers, and you say if the dimensionless number is large, then I'll get 12. If the dimensionless number is small, maybe I'll get something else. So that's the idea. I mean, it's the same thing. I mean, I don't want to solve. You can do this. This is a very standard thing. All right. So how much time have I got? Okay. Let me show you the question, and then we will discuss the answer of this tomorrow. Coming back again to Aristotle and Galileo. And what is the question? You go to a pool, and you are swimming in a pool. I mean, I cannot swim, but you have seen other people swimming in the pool. And you stop moving your body. How long do you go? Right? For So if there is a human being, DH, order of magnitude. I mean, Michael Phelps will go DH by LH is 5. You will go DH by LH is 1. Order of magnitude is 1. So this is order 1. If there is a microorganism, and this is the question I want to think about, dm, and again non-dimensionalized by lm, this is equals to how much? So dh is the size of the human, 1 meter, right? Most of the humans are about 1 meter long. And no, sorry, yeah, I'm sorry. L is 1 meter. Dh is how long do you go when you stop moving your body? How long do you coast? So d is the coasting distance. What is the coasting distance of a microorganism? Obviously, it's not 1 meter because it's very small. But so that's why I'm saying, compared to its own size, what is the coasting distance? And that will answer the question. If you think about this hard, that will answer the question, why does an E. coli need a helical flagella? I mean, why a stiff flagella at the end of E. coli will not do? I mean, actually, there's another question. Why does E. coli need so many flagellas? An E. coli has lots of flagellas. Why does it need so many? And why does it need a helical? Why does it not have a rigid? And these questions I'll answer tomorrow. Yeah, because I find them very exciting. And anyway, my time is up. So you think about this. What is dm by lm? What is d? So like dimensionless number, right? What are these numbers? And you should be able to answer it. I mean, don't try to look up on the internet. I mean, you may not get it. Like I said, answer is not important. Questions are important. If you think more time on the questions, answers will come. Maybe not tomorrow, day after, but who is in hurry, right? So Einstein is obviously, people keep talking about Einstein. Einstein gave 2 theories. First one was called special theory of relativity. That he gave in 1905 along with Brownian motion and all those things. When did he give general theory of relativity? 10 years. It took him 10 years. I mean, Einstein was very smart. And so the idea is that, and that's what Einstein himself says, that you have to spend time with problems. And like, if you want to do science, you will enjoy, I mean, you should enjoy spending time with problems. Otherwise, it can be very bad. But if you enjoy spending time with problem, and then, I mean, yeah, when you find the answer, it's very nice. So it's kind of worth it. So I'll stop here, and then we will discuss tomorrow this question basically. And this question answers a lot of questions.
So what does spending time with the problem mean?
Thinking about it for deep.
So what do you think, like you take a problem, you're like blank, how do you do this? What do you think that, like?
So I'll tell you this. Yeah, no, it's a good question. So I did my postdoc with Mike Cates. So Mike Cates is the current Lucasian Chair of Mathematics. The previous one was Stephen Hawking and so on. And so what I realized with Mike is, if you ask him a question, he will tell you the answer by connecting it to 20 things. So it doesn't mean that you leave everything and think about this problem. You keep it in your head. You remember, I don't know the answer of that question. You don't pretend that I know the answer. Like if someone asks you, how does an E. coli? So you say, because you have flagella. And then you think that you know the answer. No, you don't know, because why does it need flagella? So you keep accumulating questions. You keep accumulating questions. You know what you don't know. That's what it means. It's not that you don't just sit there and pretend that, oh, okay, I'll just solve. No, I mean, you keep accumulating questions. And what I really realized with Mike is that he can connect things so well. Because if you have thought about this problem deeply, if some other problem comes, you can think about that and bring ideas from there to solve this problem and so on. Huh? Mike Cates. His name is Michael Cates. He is the current Lucasian Chair of Mathematics. He also does, I mean, I learned a lot of things from him. Yeah, soft matter physicist at Cambridge. And yeah, he has some nice video lectures and so on. So yeah, I mean, I think it's a good question. It's just about remembering that you don't know the answer to this question. Like knowing what you don't know, kind of thing. Right. So tomorrow then.
On behalf of everyone here, I would like to extend a heartfelt gratitude to Professor Rajesh Singh for gracing this occasion with his valuable presence. Your words today about the square cube law or the Freud's law were not just informative but truly inspiring. Your insights have had a great value to our gathering, and we are thankful for the time and thought you shared with us. And especially, we have learned an important lesson today, and that is the power of questioning. So, thank you for your presence.
Swayam Prabha. Digital India. Educated India.